Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 4th, 2025, just about 5 days ago. This paper introduces a new method that reduces the computational cost of pre-training certain vision models by a factor of 2.25 times. The paper is titled, FastDINOv2, Frequency-Based Curriculum Learning Improves Robustness and Training Speed. And its approach for making large model training more accessible is really clever. The authors use a two-stage training strategy, starting with low-resolution images to accelerate learning and improve efficiency. Also, the authors shared their implementation on GitHub. If you check it out, you'll find all the shell scripts needed to reproduce their work. This includes everything for training the model on ImageNet and for running the linear probing and evaluation benchmarks they talk about in the paper. So what does this two-stage process actually achieve? Well, this table lays out the results from what's called linear probing, a method to test how good the model's learned features are. You can see FastDINOv2 cuts training time from over 16 days down to just 10. And look at the GFLOPs. That's Giga Floating Point Operations, which measures the total computation. It's more than halved. In return for this efficiency, performance on ImageNet 1K is nearly identical, and on ImageNet C, a dataset for testing robustness to corrupted images. It's just as good. This next table really breaks down how that robustness is achieved by looking at different types of image corruption. The authors are testing how each training stage by itself affects the model. You can see that the first stage, training on low-resolution images, makes the model better at handling things like fog and motion blur. But the second stage, with that Gaussian noise patching, makes it dramatically better at high-frequency corruptions, like impulse and speckle noise. So each stage creates a specific focus or bias, and combining them creates a more well-rounded, robust model. And this table shows the combined effect of those two stages in detail. It compares the standard DINOv2 with the new FastDINOv2 on the ImageNet 100C benchmark, which tests accuracy on various image corruptions. The results are pretty dramatic. Look at the huge gains against high-frequency noise, like a more than 27% jump for impulse noise. This directly shows the power of that second training stage. Overall corruption accuracy is up by over 6%, with only a tiny, negligible dip on clean, uncorrupted images. So, how does this improved focus play out visually? This figure gives us a peek inside the model's minds using a technique called GradCam. GradCam creates these heat maps, where the warmer, redder colors show which parts of the image the model is paying most attention to. On the left, you see the original DINOv2, and its focus is a bit scattered. But on the right, the FastDINOv2 model's attention is much tighter. It clearly outlines the birds and the goose. This shows the new training method really helps the model zero in on the object itself. And we can see this improved robustness from a different angle with these plots. These are what are called Fourier error sensitivity heat maps. Think of them as maps showing which image frequencies, so low frequencies for general shapes, high frequencies for fine details, cause the model to make mistakes. The warmer the color, the more sensitive the model is to errors in that frequency. You can see the original DINOv2 on the left has a lot of yellow, showing sensitivity. But FastDINOv2 on the right is much darker blue on the outside, showing it's far less bothered by high-frequency noise. So to wrap things up, what we've seen across all these results is that this two-stage, frequency-based training really pays off. FastDINOv2 manages to dramatically cut down training time and the total computation, those giga floating point operations, while making the model much more robust to high-frequency noise. And it achieves this without hurting performance on clean images. It's a powerful demonstration that robustness can be intentionally designed, not just a byproduct of massive scale. That's all for this week's AI Research Roundup. I'm your host, Alex. Thanks for listening.